Welcome to my Lab 1, Constant Velocity by Nicholas Schweiker. So a brief introduction. The purpose of this lab is to identify and explain the changes in values of position and velocity of the object in motion, and explaining it using fundamental physics principles like Newton's first and second laws. And then we're using two sets of data where we have predicted using GlowScript code to make theoretical data and experimental to analyze a video of a ball rolling using the Tracker app. And in the end, there is slight variation in the velocity and the acceleration data, but none in the predicted theoretical. So here are some of the main physics ideas. Newton's first law of physics: a body in motion remains in motion unless a force is exerted upon it. The ball is in constant motion in both the theoretical and experimental data because there is no net force, so velocity is constant. And then that applies to Newton's second law of physics: force equals mass times acceleration. No net force, so no acceleration, constant velocity, constant rate of change of position. Momentum principle: the ball has constant momentum because constant velocity and mass. Position, velocity, and acceleration can be related through calculus, and we use these models and principles of mechanics because it helps us describe the why behind the data of the object's motion. So here's the lab setup. The initial condition is the ball rolling along a flat surface at a constant velocity. When the ball is rolling, we're collecting position data over time for 1.3 seconds as the ball moves roughly 2 meters. The system is defined to be only the ball and the surface, and everything else is the surroundings. Physical error from the experiment is from the Tracker app and friction. And in the experimental setup, we rolled a lacrosse ball along a flat floor at a constant velocity and recorded the video to the Tracker app to analyze its position. This is just a video of the ball. Here in the Tracker app, you can see we have the coordinate system defined by the pink lines, and then we have the scale developed by the blue lines. And then off to the right, we have the position graph and then the data table below. So by selecting the ball, the Tracker app will automatically go frame by frame of the video and try to find exactly where the ball is, place a point, and then from there it can analyze the position and velocity. Here's the experimental model results. Of course, the velocity is up and down, but it is mostly at 1.56. It doesn't vary by more than 15%. And then on the right, there's the graph of position versus time, where you can see it is mostly linear because the ball is rolling with constant velocity. So using GlowScript, starting from top to bottom, we have the ball, trail, and origin to make the visual. And then we make the two plots of velocity versus time and position versus time to the right. And then we define the ball's mass to be 1, set the position to 0, 0, 0, give it an initial velocity, set time equals 0, set the delta t equals to 1 frame in the experimental data. Then we have a while loop that's running on time is less than 1.3 seconds. We have no net force. The velocity is not updated because it's at constant motion. And then the position is updated at a constant vector. And then time is updated. And then you have visual and graph entries. And then at the bottom, it prints the time, ball's position, and ball's velocity. And then it'll run that loop until it's done it for 1.3 seconds. And then it'll print all done. Here are the predicted results from the data from the GlowScript code. On the top right, we have the position versus time graph, which is perfectly linear. And then below that is the velocity versus time, where it's perfectly constant at 1.57 meters per second. Here is a graph of position versus time for experimental and the predicted data. The predicted is slightly higher than the experimental, but they start at the same point. And the reason why that is because the experimental, the ball is slightly slowed down because of friction, but still it is mostly at a constant velocity because it is a linear graph. Here is the velocity versus time graph for the predicted and the experimental data. The predicted is perfectly linear because it is predicted to have constant velocity because it is constant motion, while the experimental data varies a little bit, but no more by 10%. That is just because of an error in the Tracker app. If I oriented the axis different in Tracker, the data would be different. If I scaled the axis differently, it would record the ball moving much faster and much farther. If I rotated the axis, the ball would move in the y-axis rather than the x-axis, which would have the same data if the x data was replaced with the y data. If I flip the axis to make like x equals negative x, then the position would start at 0, would decrease into the negatives, and the velocity would be negative. If I moved the origin of the axis, the ball would not start at 0, 0, 0, but rather at a different point, but it would still move in the positive x direction, and the velocity vector would not change. The predicted data is created assuming no net force, but this is unrealistic because there will almost always be forces acting upon it. It is impossible to say how many pushes and pulls or number of forces are on the object in the experimental data. There are so many potential forces that could be acting upon the ball, like friction, static electricity, gravity, and normal forces. But velocity is mostly constant over the data, other than a slight decrease over time, which is likely from friction. Many other forces cancel out, like gravity and normal force, and will not cause acceleration. The purpose of this lab was achieved where the predicted data's position increased at a perfectly constant rate while velocity did not change at all. And then in the experimental data, the position was increasing at mostly a constant rate, and the velocity had some variation, which was due to tracker app recognition error, and slightly decreased over time. And that is most likely because of friction of the lacrosse ball slowing it down as it rolled in the video. And without these two sources of error, the experimental and predicted data should have been exactly the same. Overall, this lab reflects Newton's first and second law on objects in motion and the connection between forces and position and velocity in kinematics.